While this chi-squared hypothesis test is testing claims about population proportions, we won't actually be using sample proportions per se to estimate them. Instead, what this test does is it uses frequencies. Right? If we remember, a frequency is like the count, the number of times something has occurred. The proportion we can think of as like a ratio, the number of times something has occurred over the total sample size. This chi-square test is going to look at two different types of frequencies. One that we'll call observed frequencies or sample frequencies, and the other which we'll call expected frequencies. And these will be expected frequencies based on some hypothesized proportion. Let's see an example. It has been stated that roughly 50% of American households are considered middle-income families. To test this, a researcher took a sample of 800 households and found 430 are middle income. Previously, when we wanted to estimate a proportion, we found our sample size, 800, the number of successes, 430, and we used that sample proportion to test the claim. However, we're not going to be doing that. Now we're going to be using the frequency. This is what we will call the observed frequency, right? Of 800 households, we observed 430 being middle income. Well, the question now is, what is our expected frequency? For this problem, our assumption is that 50% of American households are considered middle income. So if we wanted to calculate this out, we would take our sample size times our hypothesized population proportion, right? 800 was our sample size, and our hypothesized population proportion was 0.5. Therefore, we would expect 400 out of the 800 sampled people, sampled families, to be middle income. Now, while this is what we may expect, there's variability from sample to sample, right? If you flip a coin 800 times, you're not guaranteed 400 heads. So just because you don't get exactly what you expect doesn't necessarily mean your hypothesized proportion is incorrect. Essentially, what we're going to be doing is saying, hey, how different is what we observed from what we expected? So we'll look at observed versus expected. In this problem, we observed 430 and we expected 400. So is the difference between what we observed and what we expected significant? Well, in this case, we were 30 observations off. Is this a big difference? Is this a small difference? Well, we'll see how we can determine that using this chi-square test. Now let's go over a full example. So suppose a researcher in SLO wanted to test the hypothesized distribution of high income, middle income, and low income families. It's been stated that 20% of families are high income, 50% are middle income, and 30% are low income. And they're working for a company and they want to target their product to low and middle income families. So to do this, they can run a chi-squared test. We have three groups, high, middle, low, and we want to test the proportion associated with each. So what we can do is find the expected frequency for each category based on our sample. So in this case, we observed 800 observations. We expected 20% to be high income, and we would end up with 160. We do the same thing for middle income. We observed 800 observations. We expected 50% to be middle. That's where we ended up with that 400. And lastly, we did the same thing for low income. We'll observed 800. We expected 30%, and we end up with 240. So what we'll do is we'll compare what do we observe. We'll look at these as observed compared to our expected. So for each group, I'll make a little difference. 180 minus 160. This is for high income. We'll do the same thing for middle income. We observed 430 and we expected 400. And lastly, for low income, we observed 190 and expected 240. Now, since we are analyzing all these proportions at the same time, we're going to be looking at the difference between what we observe versus what we expect. And because of this, we're going to add up these differences for each group. Observed versus expected for high, observed versus expected for low. We'll add up all of those differences between what we observed and what we expected. And we'll notice if we were to do this out, we end up with the value 0. Regardless of how many groups you have, the sum of your observed versus expected for all of your groups will always sum to 0. So we need to do some things to counteract this. So we just saw that if we summed up these differences, it sums to 0, right? We don't want that to sum to 0 because that's not going to tell us anything about what we observed and what we expect if every single time the sum is 0. So in order to counteract this, what we're going to do is square those differences. We're going to look at the squared differences between what we observed and what we expected. This will make it so it's not the case where the sum of those differences is 0. So we're going to square our observed versus expected. We also need to think about what difference is more meaningful. For instance, suppose we had group 1, so I'll just call this G1, and we observed 20 observations, expected 10. For group 2, I'll call this G2. We observed 1,010 observations and expected 1,000. The difference between what we observed and what we expected is in both cases 10. Yet, if we just look at the squared difference, 10 squared would be 100, 10 squared would be 100, they're the same. However, one of our groups is more meaningful than the other. Right? In group 1, we only expected 10 observations, yet the difference between our observed and expected was 10. We essentially saw an 100% increase. This comes out to 1. In our other situation, we expected 1,000 observations. And the difference between observed and expected was 10. In this case, we only received about a 1% difference. So it's not just about the size of the difference. It's also what we need to consider is how meaningful is that difference? How meaningful is being different by 10 or being different by a certain amount? So to represent this, we divide by what we expected to get a sense of how meaningful is the difference. We square those differences so they don't sum to 0. We divide by what we expect to get a sense of how meaningful is that difference. Is that a big difference or is that a small difference? What we've just uncovered is what's going to be our test statistic for chi-squared. We take the observed frequency for each group and see how different from it is from what we expected. But if we sum them all up, that sums to 0. So what we do is we square those differences. And then we say to ourselves, well, to get a sense of how meaningful that difference is, let's divide by what we expected. This is going to be the metric that we use to test our hypotheses. If we were to do those things that we've talked about in terms of your chi-square test statistic for this problem, we would square all those differences, what we observe to what we expect, and then we would divide by what we expected in the first place. For this group was for high income families. This was for our middle income families. And this was for our low income families. If we were to do this out, our high income quantity would be 2.5. Our middle income quantity would come out to be 2.25. And our low income quantity would be 10.42 roughly. And adding this all up would come out to about 15.17. And we would denote this as our chi-squared test statistic. Now, if we were to think about this test statistic, what values can it take on? We're looking at observed minus expected frequencies. Our numerator is always going to be positive because we're looking at the square distance, right? This is always going to yield a positive numerator. Our denominator is going to be positive. You can never expect a negative amount of observations to occur, right? You can't have negative 10 expected frequency, something like that. Because of this, you can only have positive test statistics or technically zero. You can never end up with a negative test statistic. That's not like what we saw with normal and t, right? In those distributions, you could have a negative test statistic. Chi-squared, this chi-squared test, that's not the case. You can only have positive or zero. Because of that, this test statistic is going to follow a different distribution, which we'll call the chi-squared distribution.